Okay, so our next job is to figure out how much energy a positron would have to have if it's striking an electron that's stationary in the lab in order to convert into a Z0. Now, this actually isn't a terribly easy problem if you do it in the lab frame from the beginning, and that's because the final state, Z0, cannot be stationary, because if it was, that would violate conservation of momentum in the lab frame, because your incoming positron has some momentum. The target electron is at rest. Therefore, the total momentum of the electron and positron together is not zero, and so by conservation of momentum, the total momentum of the Z0 that is produced, and it's the only thing that's produced, can't be zero, so it has to be moving. However, when you think about it, we've already done this problem, because we've started with an electron and a positron in the centre of mass frame and just had enough energy to produce a Z0. And we know that in order to produce a Z0 in that frame, the energy of the electron and the positron are both 45 GeV. But when you think about it, the statement as Z0 has been produced is a observer-independent statement. After all, you either produce a Z0 or you don't. If you do produce a Z0, all observers should agree that a Z0 has been produced. So if we know how much energy each of the electron and the positron have to just make a Z0 in the centre of mass frame, and we can take this physical configuration of these two incoming particles and convert into a frame where the electron is actually at rest, and in that frame figure out the energy of the positron, we will know how much energy the positron has to have in the frame where the electron is at rest to just produce a Z0. So we can solve the problem that way. Now that means we have to do a Lorentz transformation on the energy of the incoming positron. So that's a little bit fiddly, and you also have to remember how to do Lorentz transformations on energy and momentum. So let's do that bit first. Let's go figure that out. So I'm going to erase this stuff down here, because that's the calculation we already did. And I'm just going to relabel the energy and momentum of the electron and the positron. I'm going to give the energies a subscript E. They're both the same, so they can both have the same subscript. And I'm also going to give the momentum a subscript E. And they're equal and opposite, but the minus sign on the momentum of the positron takes care of that. So let's remind ourselves about Lorentz transformations on energy and momentum in general. If you have a particle that in some frame has energy E and momentum P, right, and you want to move to a different frame, a primed frame, where the same particle will have a different energy, total energy E primed and total momentum P primed, and the momentum of the particle is directed along the x-axis, okay, then the energy E primed equals gamma for the primed frame with respect to the unprimed frame times E minus beta CP. Okay? And the momentum P primed times C equals gamma times Cp minus beta E. So those are our Lorentz transformations. For energy and momentum between the unprimed and the primed frame. And I'll just remind you that gamma equals 1 over the square root of 1 minus v squared over c squared, where v is the velocity of the primed frame, an observer stationary at the origin of the primed frame as it zips along, as measured by the observer stationary in the unprimed frame. Okay? And when we write down these formulae, we also have this beta, which is the ratio of v over c. Beta is positive when the primed frame is moving in the direction of increasing x with respect to the unprimed frame. So that's what gamma and beta are. Now in the case of this problem here, with the primed frame we want to be in is the frame in which the electron is at rest, because after all, that's the physics. We want to figure out how much energy a positron has to have hitting a stationary electron. Now, in the centre of mass frame, the electron is moving to the right, and it has a total energy of E sub electron, which equals 45 GeV. Right? And so now let's in order to figure out the energy, now in the frame where the electron's at rest, its total energy is of course just going to be 0.51 MeV. It's going to be the rest energy of the electron because it's at rest. But the positron is a completely different story, because that positron is moving to the left in the centre of mass frame. If we're running along at the same velocity of the electron, the positron is going to be moving even faster to the left in the rest frame of that person who's running along, and therefore its energy is going to increase. And so what we want is to use a Lorentz transformation to calculate E sub positron primed, the energy of the positron, in the rest frame of the electron. So the obvious Lorentz transformation to use is the one I'm circling now, because look, the thing on the left is the energy of the particle in a primed frame, and all we have to do is figure out gamma, and figure out beta, and figure out what E and P are, which are the energy and momentum of the positron in the unprimed frame, and we can then get an expression for E primed. So that's what we're going to do next. So, let's figure out all of those things. Firstly, let's figure out gamma. Now, we know that the energy of the electron in the unprimed frame is 45 GeV. We also know that the mass of the electron times c squared is 0.51 MeV. But we also know that the total energy of a particle, in this case E sub electron, is going to be gamma times the rest energy. So that means that gamma equals the total energy of the electron in the centre of mass frame divided by mec squared. So that is the gamma factor for the rest frame of the electron as measured in the centre of mass frame, which is exactly the gamma we need for this Lorentz transformation formula. And it turns out that's a very large number, because E sub electron is 45 GeV, and the mc squared is 0.51 MeV, and the ratio of 45 GeV to 0.51 MeV is approximately 90,000, which is much, much bigger than the threshold of 7, above which we call a particle highly relativistic. Okay? So that's gamma. Now what about beta? Now I told you in lectures that whenever gamma is greater than 7, you can consider the magnitude of beta, which is V over C, to be as near as makes no difference 1. So we're going to put beta equals to plus or minus 1. It's plus 1 if the electron is moving to the right, and minus 1 if it's moving to the left. In this case, the electron, and therefore its rest frame, and therefore the prime frame's origin, is moving to the right, because the electron's moving to the right in the centre of mass frame. So beta is, as near as makes absolutely no difference for this problem, plus 1. So we've got gamma of 90,000 and beta of plus 1. Okay? So that allows us to do the calculation. And remember that method of calculating gamma from the total energy and the rest energy. That's very important. So now we've got E primed equals gamma, which we found out. Now E, we know it's E sub electron. I'm not going to write the number in yet. Right? Beta is 1, but we're just going to put it in. That's 1. Right? So as it's 1, we can just erase it actually. We can just not bother with beta because it's 1. Now C times P, if you have a particle which has a gamma factor of 90,000, you remember that E squared equals C squared P squared plus M squared C to the 4th in general. But in the case where the particle is highly relativistic, which this positron certainly is, right, because it's got 45 GeV of energy in the in the centre of mass frame, that energy is dominated by its momentum, and so you can actually neglect the m squared c to the 4th term altogether and write that E squared equals C squared P squared, which means that PC is plus or minus E. And don't forget, when you take the square root of E squared equals C squared P squared, to remember that the momentum can have a negative sign, and so this plus or minus is important. In this case, the positron is moving to the left, and therefore PC equals minus E. because it's moving to the left. This is one of the most common mistakes you get in problems where people are doing energy and momentum conservation. They forget to figure out the sign of the momentum. They typically just assume it's positive, which in this case it isn't. And so we've got PC equals to minus E sub electron, right? And that means the minus sign here cancels with the minus sign from the original Lorentz transformation, and we get that the energy of the positron in the rest frame of the electron is gamma times 2 times the energy of the electron in the centre of mass frame. Okay, now that's going to be a remarkable result, because that factor of gamma, don't forget, is 90,000. So in this case, the energy of the positron in the lab frame, which in this case is the prime frame, it's the rest frame of the electron, which is the lab now, is 90,000 times 2 times 45 GeV. So that's 9 times 10 to the 4 times 9 times 10 to the 2 GeV, which is 81 times 10 to the 6 GeV, which is an enormous energy. What that tells you is that you never want to build a fixed target accelerator to make Z0 bosons, because in order to create a Z0 boson out of an electron-positron pair with the electron at rest, because of special relativistic effects, the positron threshold energy to do that isn't 90 GeV, it's 81 million GeV. And you try getting the funding to build that thing, I guarantee you won't. So what this problem has shown you is how to do Lorentz transformation of an energy from one frame to another using the Lorentz transformations for energy and momentum. You can just as easily do the Lorentz transformation for the momentum. It's a very similar formula. We've also shown the value of making approximations. We made the approximation that beta is approximately 1. We made the approximation that Cp is approximately equal to E for a highly relativistic particle. And those two approximations made the calculations considerably simpler. And that's the end of the problem which I laid out in notes for lecture 8. And I hope that that somewhat makes up for my forgetfulness or lack of organisation in messing up my timetable and not showing up to that lecture. I'm also going to be releasing some YouTube revision lectures which I commend to your attention before the exam, and the very best of luck to all of you taking the relativity component of PHY 101. Bye!